In this video, I'm going to show you how to test 6 types of semiconductors using a multimeter. Silicon diodes, including Schottky diodes, Zener diodes, microwave oven diodes, LEDs, bipolar transistors, and MOSFETs. On my website at techcircuit.org, there's a page called Semiconductor Testing Cheat Sheet that covers how to test all these items here. Let's start with a simple diode. This is a silicon diode. Silicon diodes pass current in only one direction. When they do so, they have what's known as a forward voltage drop. For silicon diodes, typically it's going to be somewhere between 0.4 to 0.8 volts. And the banded side is the cathode and the non-banded side is the anode, as per the image in the corner of the screen. And so that the black lead of the multimeter you would put on the banded side, and the positive lead you would put on the other side. Your meter measures the forward voltage drop across that diode when it forward biases it. In this case, we have 0.44 volts. When you reverse it, all diodes have a reverse breakdown voltage, but it's so high it could be upwards into the thousands of volts. The multimeter is unable to read that. So this is a typical reading that you will get with a silicon diode. Your forward voltage drop when it's forward biased, and then your reverse bias reading will be OL, which means open loop or out of range. So the maximum that most multimeters can read for a diode check is somewhere around 2 volts. So the reverse breakdown voltage is much higher, and that's why you get OL. This is a Schottky diode. This is typically used in high-speed switching applications and sometimes in rectifiers because of the fact that it has such a low voltage drop. Schottky diodes can be in the range of 0.1 to 0.4 volts typically. This one here is 0.128. When I reverse it, you get OL again. So again, we're putting the positive red lead on the anode, the non-banded side, the black lead on the cathode, and we get 0.128. This is a typical reading for a Schottky diode, and that is a good reading. Now when you're testing a diode in circuit, you're going to get a reading like this. This is typical reading. But when you reverse it, you would expect to be open loop, but not in this case. This particular diode is in parallel with the coil of this relay. This is protecting the driver transistor here from flyback voltage. So, but the key here is you have asymmetry. This reading is lower than that reading, and I would deem this probably a good diode if I'm in testing them in circuit. Here's another flyback diode here protecting this driver transistor of this relay coil. Got 573, that's in the range. If we reverse it, then I'm getting 1.2 volts, that is. So, but there's the asymmetry there, so that I'm going to deem that as being a good diode. Now for a Zener diode, their intended application is to be used in their reverse breakdown mode. So for Zener diodes, they're going to read like a regular diode when you put the black lead on the banded cathode side. When you reverse bias it though, when you reverse it, you get OL. That's because most Zener diodes have a higher voltage breakdown than your multimeter can read. So you can't just use your multimeter. You have to put a current limited voltage across it. And how you would do that, get a couple of batteries. You're going to put a 1K resistor in series with the voltage, and we're going to test the voltage across the Zener diode when this 1K resistor is limiting the current. So I'm going to go ahead and construct this at time lapse. I've got this put together. You can use anywhere between a 1K to say a 5K, 4.7K is the more standard value. So any resistor in that range will be okay. What you're going to want to do is you're going to put your voltmeter on voltage, DC voltage. And you're going to connect the red lead, in this case, which is a positive one. Positive one is the small side of the 9-volt battery, and the negative is the large side. and you're going to put the other side, in which case the negative I've got here is green. You're going to measure the voltage of the battery. Okay, I just had to switch that battery out because one of them was bad. So you're going to hook the green lead to the negative side, and the meter is going to show you the total voltage that is supplied by this current limited voltage source, and it's 18.47 volts. Now, for the Zener diode, I'm going to put the banded side on the positive and the other side on the black lead. So this is probably a 5 volt Zener diode here. Let's test yet one more. So for this I'm getting 17 volts. This is probably a 17 volt Zener. Now this jig here, we have two 9 volt batteries in series, gives us about 18 volts. You're only going to test Zeners up to about 17 volts like this one right here. If you want to go higher, you put another one in, but just know that you're going to get 27 volts. You can actually get a tingle, slight shock from that, so you might want to put gloves on if you're going to go over two 9 volt batteries. If you stack batteries, you could actually get up to lethal voltages ultimately. So that's Zener diodes. Now for the microwave oven diode, we're going to use this test jig because microwave oven diodes are stacked diodes. That's how they get such a high reverse breakdown voltage into the thousands and thousands of volts, which is suitable for a microwave oven circuit. Now these here have because they're stacked, they have a forward voltage drop of somewhere between 4 to 12 volts. I've seen them as high as 11 volts. So that's why I use two 9 volt batteries. You'll see a lot of videos online where you can test microwave diode using a 9 volt battery. However, there are some that are over 9 volts, so you may not be getting an accurate reading. And also, those ones you see online, they're not using a current limited voltage source like what we're doing. This is a proper way to do it here. The ones you see online, the reading that you get, when you just put a multimeter in series with the 9 volt battery and the diode, you're just going to get a reading that is dependent on the input impedance of the actual multimeter, and it's going to vary, and it is so high that you may not get an accurate reading. So this is really the proper way to do it. You're going to actually put the banded side on the negative as opposed to the Zener diode. You're going to test this like a regular diode. And on this one here we have an 8 volt drop across this diode. It's almost to the point where you would have to have two batteries. So barely one 9 volt battery would be able to cover this. So there's a case in point regarding wanting to use two batteries. Now of course if you reverse it shouldn't make any difference because the reverse breakdown voltage of a microwave oven diode is up there in the thousands and thousands of volts. Just for reference, instead of putting this jig together, I actually did create a device here. This is essentially two 9 volt batteries and a current limiting resistor. I also put an LED. This is basically the same thing, but this is portable. And when I go to test, there's a link to how to do this. So I made a video on how to build this. I'm going to go ahead and test it with this. In this case, you can just go ahead and you can use the multimeter, but this actually gives me a green light to tell me that the microwave oven diode is good. And if I reverse it, there's no green light. That's because it's reverse bias. Now, if you've got a green light both ways, the microwave oven is bad. Microwave oven diode is bad. That means it's shorted or leaky. If you get no green light, no conductivity either way, then that microwave oven diode is bad as well. But it's very rare for microwave oven diodes to fail in an open condition unless they're cracked and broken open. Typically, when they fail, they end up being leaky. They'll conduct current in both directions or just be a dead short. So anyway, this device could be used to test Zeners. It could be used to test the microwave oven diodes. This can only be used to test Zeners up to 17 volts, like with this test jig right here. Again, there's a link to this, how to build this, in the video description. So back to the semiconductors now with LEDs. LEDs are also diodes, as per the name of them, light-emitting diodes. So LEDs, they're going to have a forward voltage drop of somewhere between 1.2 volts and higher. Now, if you get a higher power LEDs, then you are going to need this test jig here. But let's disconnect the battery, this current limited voltage source here. Just put it on diode check. Now, for diode check is suitable for standard panel mount LEDs like these. Now, the cathode or the negative side is typically going to be either the short lead or the side that's flattened on the diode. It's not always the case, but most of the time. Or if you look inside the diode, the largest part of the structure is usually going to be the cathode or the negative side. So let's put that on this, and we'll put the red lead over here, and we're getting 1.8 volts. That's about what we get if we use this test jig too. This test jig you can use if you don't have a diode check. Most multimeters do have a diode check though. And also, if you do this, sometimes you'll see a little bit of a glow, slight amount of glow. But the output resistance of this diode check is very, very high, so it's not going to be very noticeable. Now, if you reverse it, you shouldn't get anything. It's going to be higher. But I will tell you that reverse biasing a diode is not good for it. It may tolerate it a few times, but technically it's not good to reverse bias a diode. So you want to probably just make sure that you have the polarity correct. Here's another one here. This is a large diode. The internal structure here indicates this is the cathode side. Also the short lead does. So we're going to put the red lead on the anode here, black lead on the cathode. Now this one here, we're not getting a reading. I would say that's because this has a higher voltage drop than what the meter can handle. So we'll go ahead and go back to that one, and we'll hook the test jig up to that one to see if we can get a reading on it. This one here, this one has the same, this one's cut, the leads are cut on this, but looking inside of the diode, it looks like this is the larger side of the structure here. So I'm going to deem this one as being the cathode. This is your anode, and I'm getting 1.6 volts on this one here. Okay, now let's go ahead and put this back on voltage, DC voltage. Hook our test jig back up and see if we can get some kind of a reading on this diode here. So this is your positive side, this is your negative side. Okay, so this is a high-powered diode here, and they often have a voltage drop, forward voltage drop of about 3 volts. I was going to go ahead and do a test on a high-powered diode separately, but I don't need to now because this is one. It has a forward voltage drop of about 3 volts. As you can see, when we hook our jig up to it, it does light it up, and we got a 2.9 volt voltage drop on that. So that's how you test higher powered ones. You got to have a test jig like this for it. So we're not going to need this test jig anymore for the rest of this video because we're going to be doing bipolar transistors and MOSFETs. You don't really need it for that. But again, this is a simple thing to put together. It's a resistor and a couple batteries and some jumpers. About 1K to 4.7K is about right. So let's get rid of that. Okay, bipolar transistors. This here is the extremely common 2N3904 transistor. I actually have the website domain 2N3904.com, and I'm building that out right now to have all kinds of projects for how to build what you can build with 2N3904 transistors because they're so common. There should be a diagram in the corner of the screen. As far as the pinout of this, that is an emitter, base, and a collector is what the bipolar transistors have. Is their pinout, emitter, base, and collector. On some of them it's ECB or emitter, collector, base. But also in the corner of the screen you'll see how this transistor looks to a multimeter. It's not how the transistor looks when it's actively used in a circuit, but how it looks to a multimeter is 2 diodes that are back to back. And for the NPN transistor, the P, the center of the nomenclature, refers to the base, and that's the common, and that's what you're going to use. You're going to use the NPN transistor. You're going to use since it's a P, you're going to use positive for the red lead on the base, and we're going to put the black lead on the emitter. Let's put it over here on diode check, and we get a reading on this meter here. This Fluke. Oh, there's a link to this meter in the description, by the way. This is a really good meter. Appreciate you using the affiliate links because they help support this channel and allow me to make more great videos like this one. So anyway, this is what you would get when you connect it in this manner. You're forward biasing what looks like a diode to the multimeter. Now you're going to, since the base is common, you're going to leave that there. You're going to come over to the collector and you're going to get the same thing. Now if you reverse it here, you're not going to get anything, and that's what you should get. If you get anything, it's probably a bad transistor. Now this is a PNP transistor. This is the 2N3906, which is the very extremely common complement to the 2N3904. the base. This is a PNP transistor, as shown in the corner of the screen. The pin out. Since the base is in, it's negative. It's going to be your common. You're going to put the black lead on the center, and you're going to put the red lead on the emitter. You're going to get a reading there. And you also, referencing that to the collector, you're going to get a reading. Now, if you reverse it, you get nothing, and you get nothing. That is what you should get. So these are two transistors. They're good transistors. Now, if you're testing transistors in circuit like this, you may get various different readings. If you want to find out which is the base in the collector, you just have to kind of poke around and find what you turns out to be the common. So this is an in-circuit test here. All right, we got a forward bias reading there. All right, so this is an NPN transistor here. Okay, now if I reverse it, if it's in circuit, you may actually read something. In circuit, you may actually read something. In this case, we're reading 1.9 volts. So you think, okay, well, if this is out of circuit, it would be a bad transistor because it's leaky. But you have other components in here that they're in parallel with this reading. You're also picking them up. So that's why you're getting that. But the key here is you got asymmetry. You got a very good reading there. So we have this base to collector reading here, but if you reverse it, it's much, much higher. So if it's in circuit, you have this type of asymmetry, it's probably a good transistor. But if you're just unsure, you can pull a pin out and test it. Okay, the last semiconductor that we'll test in this video is the MOSFET. This is an N-channel MOSFET here. And MOSFETs, the current flow, conventional current flow that is from what's known as the drain to the source. The pinout is gate, drain, source. And for that current to flow, the gate has to be biased positively with respect to the source. So to test an N-channel MOSFET, you'll put it on diode check here. And you will put your black lead on the source, which is this one here. There's going to be a pinout in the corner of the screen there. And your red lead on the drain. Now you're not going to get a reading, okay? So what you need to do though is leave the black lead on there, take your red lead and touch the gate for a few seconds and let it charge positively with respect to the source. Then come back over to the drain, and then you're going to get some conductivity. You'll see conductivity. This tells me that this MOSFET is properly working here for the most part. Most MOSFETs, when they fail, a lot of times they'll be leaky or short out, and most certainly they're not going to exhibit this behavior during a test. But as far as their failure mode, oftentimes it will be when you just do this test here without biasing the gate, you'll get a very low reading, and if you reverse it, you also get a reading too. So that's how you test an N-channel MOSFET. This is a P-channel, which is a complementary function, you might say, of the N-channel in terms of current flow and biasing. So for the P-channel MOSFET, the gate, non-intuitively, the gate needs to be negatively biased with respect to the source. So to test a P-channel MOSFET, the pinout of which is going to be in the corner of the screen there. Now for a P-channel MOSFET, the current flow, by the way, the conventional current flow is from source to drain. That's why we are putting red lead on the source and the black lead on the drain. By the way, on both of these MOSFETs here, the case is also the center lead. If I touch that center lead, I'll get full continuity. So this center lead is also continuant with the case right there, by the way. So I can just use the case if I wanted to. Anyway, so we'll put the red lead on the source, black lead on the drain, and just like the other N-channel, we get no conductivity. Now, in order to bias this, we'll take the black lead and we're going to, in a sense, negatively charge this gate. We're going to bring it down so that it's biased below the source. That's what you need in a MOSFET to have it to conduct. Then we'll bring this back over here, and we have conductivity. So We do have conductivity by doing that, and that tells us that this is very likely a good MOSFET. So that's testing MOSFETs there. So that's testing 6 different types of semiconductors with a multimeter. Again, there's a quick reference on techcircuit.org, a link to which is in the description to a semiconductor cheat sheet that shows how to do all these. And I do have to say that this is for demonstration purposes only. You want to be especially careful when you're testing microwave diodes. That means you're probably working on a microwave. Microwaves have extremely dangerous high voltages, and really it should be done by qualified technicians, but their capacitors can store 4,000 volts and can be lethal. So I do have to mention that, and proceed at your own risk. Hope this video has been helpful and informative. If so, please give it a like and subscribe to this channel.